Hi everyone, my name is Fabio Banfi and I'm presenting anonymous symmetric key communication, a joint work with Ueli Maurer. In our paper we study the anonymity of probabilistic encryption, PE, and probabilistic authenticated encryption, PAE. These are on the syntactic level the same object, and mathematically they are defined by a distribution over the set of keys K, a probabilistic function from the set of keys K, the set of messages M, into the set of ciphertexts C, and finally by a deterministic function from the set of keys, set of ciphertexts, into the set of messages plus a special symbol bottom which encodes invalid ciphertexts. So note that here we are not considering nonce-based schemes. Why is this the case? Well, recently Chan and Ragoway actually did study anonymity of this other kind of schemes, and there they show that nonce-based AE can actually not provide anonymity. In fact, what they do is to provide a compiler from any such scheme which generates a new scheme of different syntax, which they call ANAE, which does allow anonymity, does provide anonymity. But arguably this new scheme is less efficient than the base nonce-based AE scheme. So this sets the stage for our work, because here we show that PE and PAE are actually better suited for anonymity, since such a transformation is not at all necessary. They can provide anonymity right away. And moreover, actually PAE, for example, also closely captures some real-world implementations. In fact, if we consider the nonce-based AE scheme of AES GCM, which is deployed in TLS 1.3, we see that there actually the nonces are randomized, which means that mathematically we can model this kind of scheme as a probabilistic AE scheme rather than an AE. So in particular, this also implies that our results apply to this subset of NAE schemes. So the conventional security notions of PE and PAE imply that PE should achieve some form of confidentiality, and that PAE should achieve some form of confidentiality plus authenticity. How do we define such security notions? In the literature, what one usually does is to define a game-based security definition, where an adversary must win some sort of game, which is usually phrased as a bit guessing or a search problem. But it is also possible to formulate such definitions in terms of a distinction problem, as we will actually use in this work. On the other hand, one can also instead define security via a composable definition, which is in nature simulation-based and is also modeled as a distinction problem, usually between a real and an ideal world. And we will also see that these two kinds of security definitions are actually closely related. So let me now introduce the concept of cryptographic systems that we use extensively to define security notions in our work. First of all, for a key sampled according to the key generation distribution, we define the system EK that on input a message M outputs a fresh encryption of such message according to this fixed key sampled according to the generation algorithm. Then the system DK on input a ciphertext also outputs according to this key the decryption of such a ciphertext. We also define a system EK$ that on input the message M samples a new uniform message of the same length and returns the encryption of this new message instead. We need also a system D bottom, which on input any ciphertext always outputs just a simple bottom. And finally we define a system $, which on input a message M outputs a ciphertext, a pseudo-random ciphertext of the same length of a regular encryption of the message M. Finally, we use this notation to define when two systems S and T are computationally indistinguishable, which means that for any efficient distinguisher, the distinction between S and T succeeds with probability negligible in some security parameter, which we ignore here for easier presentation. Now let me show you how usually security of PE and PAE is defined in literature. So for PE, we have the notion of INDS, which usually is defined as a bit guessing problem, but can also be defined, as I mentioned before, as a distinction problem, namely the distinction problem between the systems EK and EK dollar. On the other hand, for PAE, we usually have two notions that have to be satisfied by such a scheme, which can also be shown to be equivalent to one single notion. These two notions can be defined separately as a bit guessing problem plus a search problem, and the unified notion of INDS-CCA3, which was introduced by Shrimpton, can be also modeled as a single distinction problem, namely distinction problem between an encryption system and a decryption system, and a fake encryption system and a fake decryption system. And the implicit assumption in such definitions is that the setting where such a scheme should be used is the setting where there is one sender, one receiver, and one eavesdropper. On the other hand, composable security definitions of PE and PAE work as follows. We need to define some resources. First of all, we define a key resource, which defines three interfaces, one for the sender, one for the receiver, and one for the adversary. And this key resource simply samples a key according to the key generation scheme and outputs such key to the sender and the receiver, and outputs nothing at the interface of the adversary, E. Then the second resource that we need to define is an insecure channel, which allows the sender to input a message which is output at the adversary, and allows the adversary to input a message which is not necessarily the message that the sender input, and such message is output at the receiver interface. Then we have an authentic channel, which allows the sender to input a message, which now will be output by both the interfaces of the adversary and the receiver. And now the difference from this channel and the previous one is that the eavesdropper, the adversary E, cannot input a message anymore. So in particular, the receiver has the guarantee that the message that he sees is the one that was input at the sender interface. And finally, the secure channel is similar to the previous one, except that now the adversary, the eavesdropper, can only see the length of the message, not the message itself. And using the constructive cryptography framework, we can define composable security definitions for PE as follows. Namely, we define such a scheme secure when it constructs the secure channel from the key resource and the authenticated channel resource, which more formally we can define as follows. Namely, as the existence of a simulator such that the resource which results from applying the encryption to the key and the authenticated channel is indistinguishable from the secure channel plus some simulator that simulates the adversary strategy. On the other hand, for PAE, we similarly have a composable definition where we define security in terms of construction of a secure channel, now from the insecure instead of authentic channel, and the key resource. And again, formally, we can define this as follows. Now we can easily see that game-based notions actually imply the composable ones. Namely, if a PE scheme is INDS secure, then it will imply the construction of the secure channel from the authentic channel and the key resource. Formally, we can write this as this. If these systems EK and EK dollar are indistinguishable, then there exists a simulator such that the resource resulting from applying probabilistic encryption with the key resource on the authenticated channel is indistinguishable from the system of the from the resource of the secure channel, where we simulate adversary strategy at the adversary interface. And similarly for PAE, we see that in CCA3, the regular game-based notion for authenticated encryption implies the composable notion of constructing a secure channel from the insecure channel and a key resource. And we can also again model this, write this more formally as follows. Now we note that actually if we think of the internet, for example, in the real world PE and PAE are usually used in a multi-user setting, namely one where there are some number of senders which we generalize to some number n, and which in this presentation we keep fixed to 2 for easier presentation, and one receiver and one eavesdropper. So we can think of this as the case where many people connect to the same server. In this case, we actually need to enhance the security definitions that we just saw in both the game-based setting and the composable setting. And to do this, we additionally introduce the concept of indistinguishability of keys, IK. For probabilistic encryption, we now define a new game-based notion as a distinction problem, where a distinguisher gets not one but two different oracles or access to systems. The first system represents the encryption for some key, and the second for some other key, which are independent. Whereas in the other case, the distinguisher gets access to two systems which encrypt messages with the same key. And on top of that, they also actually encrypt random messages. So this notion captures both confidentiality and anonymity for PE. On the other hand, for PAE, we similarly define a new notion as follows. We have, again, two sets of pairs of systems, one implementing encryption and decryption for a key and the other for another independent key in the real setting. And in the ideal setting, we have, again, two pairs of systems, but where the key is the same. And also ciphertexts, plaintext in encryption are replaced by random plaintexts. And decryption actually always returns bottom. So in particular, this distinction problem models confidentiality, authenticity, and also anonymity for probabilistic authenticated encryption. We can also see now that we have defined these notions that a stronger version of indistinguishability of ciphertext called IND$ in the literature, or also pseudorandom ciphertext, implies anonymity. So more precisely for PE, we have that if the scheme satisfies the stronger definition, which can be defined formally as follows, namely as the indistinguishability of the system EK and the system $, then such scheme also satisfies anonymity plus normal confidentiality, as we saw in the previous slide. And for the case of authenticated encryption, we have that if the scheme satisfies the stronger definition modeled as follows, it will also satisfy this anonymity and security notion that we just saw for PAE. And what this means is that if we have a nonce-based AE scheme which uses randomized nonce and is proven to be IND$ secure, then we actually proved that this scheme provides anonymity already. We also show another important result, namely that the paradigm of Enc-then-MAC, which is used to transform an encryption scheme plus a MAC scheme into an authenticated encryption scheme, preserves anonymity. And what we mean is that if we have a PE scheme, which is has indistinguishable ciphertext and indistinguishable keys, and we have a MAC scheme which is unforgeable and also has indistinguishable keys, then the resulting encryption, authenticated encryption scheme will also have indistinguishable ciphertext and indistinguishable keys. We now turn the attention to the composable definitions for anonymity, and for this first we need to adapt the resource that I presented before. So for the key resource now, we model the case where we have two senders, So this will be modeled as follows. Namely, we sample two keys and we output the respective keys to the senders, and we output both keys to the one receiver. For the insecure channel, we allow the two senders to input messages, which will all be output at the adversary interface. And in particular, note that at the adversary interface, the information of who the sender is not published. For the authenticated channel, we have, similarly as before, an interface where a sender can output a message to both the eavesdropper and the adversary and the receiver, but this is now for two senders. And we adapt also the secure channel in a similar way. Note that in earlier work, it was already shown that the MAC schemes which satisfy indistinguishability of keys, or anonymous MACs, already provide the construction of the anonymous authentic channel from the anonymous insecure channel and this multi-key resource. In that same paper, it was also shown that one can use, again, anonymous MACs to construct the anonymous secure channel from the anonymous authentic channel, but this construction was very inefficient. They also showed how to realize the anonymous secure channel from the anonymous insecure one, again with probabilistic MACs, and again this construction also was rather inefficient. We now give the new security definitions of composable anonymity, again using constructive crypto, and we state that a probabilistic encryption scheme is secure and anonymous if it constructs the anonymous secure channel from the anonymous authentic channel and a multi-key resource. Formally, we write this as follows. And also we define secure composable anonymity of PAE by stating that a PAE scheme is secure and anonymous if it constructs the anonymous secure channel from the anonymous insecure channel and the multi-key resource. Again, formally defined as follows. And finally, we see how the game-based definitions for anonymity imply the composable ones. We show in our paper that if a scheme PE satisfies indistinguishabilities of ciphertext and keys, then it allows the construction of an anonymous secure channel from an anonymous authenticated one and a multi-key resource, formally represented as follows. And we also show that a PAE scheme which has indistinguishable ciphertext and indistinguishable keys allows the construction of a secure channel from an even weaker resource, namely the anonymous insecure channel and the multi-key resource, formally written as follows. So in conclusion, we provided game-based anonymity definitions for PE and PAE, and we saw the following two results, namely that pseudorandom ciphertext, or in $security, implies anonymity. And this is important because it shows that NAE schemes where randomized nonces are used already provide anonymity. So in particular, no transformation is needed for such schemes. And also we show that the Enc-then-MAC paradigm preserves anonymity. So if the two base schemes provide anonymity, also the resulting authenticated encryption scheme will, on top of course, confidentiality and authenticity. We also provided composable anonymity definitions of PE and PAE that arguably provide a better understanding of the application of such schemes, which is namely a setting of where there are many senders and one receiver. We also show that such notions are implied by the game-based definitions. And finally, we also saw that they allow for more efficient protocols than it was known before. So this is all. Thank you very much for your attention. And in the next slide, I show the references.